Okay, so I'm looking over and I realize that I didn't do 28, I did 29 already. 28 is one where we're looking at this astronaut as he's traveling in a circular orbit, and we want to try to kind of figure out what's going on there. Essentially, if he's traveling in a circular orbit, he's falling. And so he's always falling, and there's an acceleration that's associated with that because we're traveling kind of that circular motion. And we're changing our velocity, or changing our direction, so we're changing our velocities. I eliminate essentially the two low ones because I know that those are not going to be right. And then I said, well, it's got to be close to 9.8, and so it's going to be a little bit less than that. Originally, I started to do a gravitational one and realized that I didn't, at least on the problem that they gave me, I didn't have a what the mass of the Earth was to try to do this, and so that wasn't a fair assessment to try to go that route. So I did a logic reasoning on that one to get the answer of D. Number 30, we're looking at a mass hung on a spring, and we're looking at how it stretches. It oscillates. Okay, so you hang a mass on a spring, it's going to go bouncing up and down. And so I started to look at it in terms of the weight, or its mg is equal to that force that's the spring force. And then I did a little rearrangements to get those two values. And actually this was, so the period would be proportional to either of these two. And this is actually from the formula sheet. Both of those were given, at least in the one that I had. And so then I said, well, it's got to be proportional then to the D over G as my relationship. Okay. Moving on to 31. We look at 31, we have this picture up here, and this is our original moment arm. So in other words, our distance that we are away from our point of rotation by that force. And they're looking for one that's going to be equivalent to that. And so I have to just look at the way these forces are. And this force is going the wrong direction, and this force has moved in some, and the distance has changed, but they left it at the same force. And so then I'm down to these ones, which were both 2F, so they doubled my force, kept my distance the same, but I needed to then have it in terms of an angular components. This one is the one that I actually use my angle of 60, find the cosine. Cosine of 60 is 1/2. And so it's half of that, and that's why it made it even. Number 32, we have the body is moving, we have potential energy, so we have a potential energy function, okay? And then to get to my force function, I do the derivative of that. So the derivative of this function is this function, which is my force function. And then I just solve for by substituting in what I'm looking for. Because I'm looking at a certain position, x equals 3. Number 33, we've got a rock dropping from the tower, and we're looking at how fast is it going when it hits the ground. Oh, I gotta go down here to look at where my work is. Okay, so my 45 was here, and then I figured out the amount of time. It was 3 seconds. 3 seconds times that gave me a velocity. Kinematic problem wasn't too bad. 34, the objects of equal mass hung on a spring. Okay, so I'm looking at this in terms of my spring, and how do those oscillations relate, or how does the period relate? So I set this up where this is my one, and I said K is for the greater, and so if this greater one is bigger here, it makes this one smaller, so I get a smaller period, shorter period based on a greater K value. And so that's how I picked my answer for that one. This one said longer. This one talked about frequency, and the other two talked about amplitudes. Number 35, we've got our satellite that moves in a stable circular orbit. So again, we're back to gravitational, or law of universal gravitation. Plug in some values. Look at this in terms of centripetal acceleration. So I used v squared over r for my centripetal acceleration. Solved then for v, and got down to that answer doing my algebra. And that is the multiple choice test from 1988. I hope that this has been helpful. If you have ones in particular that I kind of didn't explain it well enough for you, or you kind of got lost in my explanation, come in and I'll try to talk to you about it in a little different fashion. All right, good luck.